Hello Biotechnicans, this is Pallavi Poojar from Biotecnika, and previously we have discussed few many important questions that is also with respect to NEET 2022. So we are going in detail that two question paper. So now this is my last day for the question paper discussion series, right? So before that, just let me wait for 1 to 2 minutes. Then at least today, definitely are going to enjoy the session. Okay, so. And whatever we are going to solve the questions, that too in detail, it will be like how you are while giving mock test, how you prepare for the examination, and this will be very very helpful for your next batch student, that is 2023 NEET examination students. Okay, so just without wasting time, let us start this question paper in detail solution part. So the next question means today's first question is regarding the lone pair interaction. So the question is like this: among the following, which one will have maximum lone pair electron repulsions? That too. So four options are being given: SF4, XeF2, ClF3 and IF5. So four options they have given. So overall, first if you want to know regarding the lone pair of electrons on the central atom, so first thing you have to know regarding the hybridization. So in SF4, what is the hybridization of sulfur, and in XeF2 xenon, and ClF3 where chlorine, and lastly IF5 where iodine. So this question you can answer only if you know how to approach, means in what way you can get your hybridization concept with respect to each and every molecule. All right, so just let us look at the answer first, then I'm going to in detail solution. So the answer for this question is option B. So option B, we have there where we have the XeF2. All right, so now coming to your in detail solution part, you have SF4, and where the electronic configuration you have to look at the sulfur, right? So sulfur, where its valence electronic configuration, we write it as 3s2 3p4. And now coming to your next molecule, you have that is XeF2. All right, so XeF2 where xenon, you have to look its valence electronic configuration, and its valence electronic configuration is 5s2 5p6 we have. And nextly you have your ClF3, right? So ClF3 you have, that is chlorine. Its valence electronic configuration we have, it is 3s2 3p5. So only one electron is left in order to satisfy its valence, right? So if attains one electron, then it will be just attaining the noble gas configuration. All right, now coming to your last one, you have that is IF5, right? So IF5 where you have the iodine, and its valence electronic configuration will be 5s2 5p5. All right, so now just let us look at its remaining part, how we can get each and every molecule hybridization. Now coming to first, what you are having SF4, right? So just let us consider you have SF4 now. So coming to SF4, so sulfur, which was having the configuration as, the valential electronic configuration as 3s2 3p4. All right, so now we have its ground state electronic configuration as 3s2 3p4 and 3d0. So in s orbital we have 2 electrons, and in p orbital you have 4 electrons. So 4 electrons, how you are going to show? You are going to show like this, and in d orbital you have 0 electrons. All right, so why I have considered d? Because in next step, where when you consider the excited state of your SF4 molecule, so overall just let us consider the sulfur electronic configuration. Now 3s2 you are keeping as it is, but one electron from the p orbital will be exciting to your d orbital. So now you have 3 electrons here, all right, and 1 electron here. So in d orbital I am going to show 1 electron. So in each and every half electron wherever you have, so one electron will be donated by fluorine, and it will be binding to sulfur. So now you have sp3d. So you have your hybridization as sp3d. But the thing what you can see, in 3s orbital you have 2 electrons, in the sense in SF4 molecule you have 1 lone pair, right? So you have 1 lone pair. So how you can show the structure? You can show like this, that is SF4, in the sense everywhere you have 4 fluorines. Now in one orbital you have one lone pair. Okay, so one lone pair you have. Now you got answer for SF4, it will be one lone pair. Okay, now your duty is to try to find out with respect to the remaining molecule. So what and all they have given apart from SF4. So with respect to ClF3, let us consider first. Okay, so with respect to ClF3, you are going to consider its valential electronic configuration, and apart from that its excited state. So in ClF3, okay, so in ClF3, what is your central atom? It is chlorine. So with respect to chlorine, its configuration will be 3s2 3p5. All right, so now we have its ground state electronic configuration in p orbital and d orbital. Just we are going to show overall. Okay, so now with respect to excited state also, the three p orbitals and d orbitals I am going to show. So what is the configuration you have? That is 3s2 3p5, 1 2, again 1 2 3 4 5, right? So you have 5 electrons in p orbital, so this will be your 3s, this will be your 3p, and this will be your 3d. Okay, so 3d is under 0, in 0 where we have no electron in its orbitals, right? So considering its excited state, so similarly here also you are going to excite one electron to your 3d orbital. So what molecule you have? You have ClF3, right? So if you excite here, so what will be remaining? 2 electrons in 3s orbitals and 2 electrons in 3p orbitals, again one electron in each 2p orbitals and 1 d orbital. So now what you can consider overall? So 1 electron will be donated to each orbital. So fluorine can bind to these 3 orbitals. All right, so what you can see, this will be sp3d again, right? So where you have sp3d hybridization with respect to your ClF3 molecule. Now what you can notice, that there existence of one lone pair here, second lone pair here, right? So if you want to draw the structure with respect to your ClF3, you can show like this. So the 2 orbitals where it will be having one lone pair, all right, and it has T-shaped molecule, right? So it is T-shaped, so where you have 3 fluorine. All right, so this is what with respect to your ClF3. So what you have noticed, in ClF3 molecule you have 2 lone pair. Okay, so in ClF3 you have overall 2 lone pair. Now coming to your next molecule, what they have given. So they have given with respect to your XeF2 molecule. All right, so with respect to XeF3 molecule, how many lone pairs you are going to get? Just you are going to consider under hybridization concept application part. Okay, so just let us consider with respect to XeF2 molecule again, and at last we have your IF5, right? So coming to your next molecule is XeF2. So in XeF2, you have your central atom as xenon, right? So xenon, what is its electronic configuration? That to valential electronic configuration, that will be 5s2, 5p6, right? And 5d 0. So we are going to considering the orbital because we are going to excite the electron to the d orbital. Now coming to its ground state electronic configuration, we have this is what the 5s we have, and this is your 5p. Okay, and you have your 5d orbital. All right, so you have your 5d orbital. I'm going to consider now under excitation state, electrons will be exciting to the d orbitals and you are going to get different hybridization. So just let us consider its ground state where you have 2 electron in its s orbital, that is 5s. In 5p you have 6 electrons, so 6 electrons I am going to show, 6 electrons here. So 5d will be vacant. Now under excitation state, what happens? This electrons will be exciting here. So how many you have? You have only 2 fluorines which are attached to central atom xenon. Now coming to your 5s, you are keeping as it is, and 5p where 2 electrons as it is, 2 electrons as it is. So just you have excited one electron, right? So after that, what you are going to show, 1 fluorine will be binding here, 1 fluorine here. So both are donating each 1 electron, and it will be forming what hybridization? It will be again sp3d. Okay, so which type of hybridization it is? sp3d. But what you can consider, how many lone pairs are present? 1 2 3. So in XeF2 you have 3 lone pairs, right? So you have in XeF2 in XeF2 you have 3 lone pairs. So what is the exact structure of this XeF2? So XeF2 you are going to show at the center xenon, right? So and here you have your 2 fluorine and you are going to show 3 lone pairs. So 3 lone pair sets you are going to show. So this is what the structure with respect to your XeF2 molecule. And right now we know the answer, it is XeF2, but we have to confirm once again with respect to IF5 also, right? So just let us go with respect to your IF5 molecule. So what exactly the hybridization you are getting and how many lone pairs you can get in IF5 molecule. All right. So coming to your IF5 molecule, so just let me consider here. So in IF5, what is the central atom you have? That is IF, that is iodine, right? So iodine you have. And in case of this, what is the electronic configuration with respect to iodine? That is valence shell electronic configuration. That will be 5s2 5p5. So 5s2 5p5 you have. So now you are going to just modify a few things. So in case of 5p orbital, you have only one electron less, because previously we have considered xenon. So xenon will be coming before, before group 18, group 17 will be coming. So under group 17, you have this iodine. All right. So now just I have modified this electron configuration with respect to your iodine. Okay. Now just let us consider with respect to the excitation. So how we can show. So under excitation state with respect to iodine, so just I am going to show. Okay. So you have 5 p orbitals, right? So p you have. So one electron. So here just what happens with respect to this, the electron will be keeping as it is here. Only the thing, this electron is shifting here, right? So you have shifted one electron. All right. So you have 3. So 5f, that is IF5 you have. So out of 5 fluorine atoms, 3 fluorines can bind to each, one iodine. So now what we want, again we want one more electron, right? So because of that reason, what happens, this orbital where the 5p orbital which is having 2 electrons, so one of the electron will be exciting to your next 5d orbital. So again I am going to show here, and then just I will erase this electron here. Okay, so now how many you have? So 5 electrons you have, right? So in p orbital you have 3. All right. So each fluorine will be donating one electron, and it will be forming bond with respect to your iodine. So again, what configuration, what hybridization you have here? It is sp3d2 hybridization. All right. So but what you can consider, that you have only one lone pair here, right? So you have only one lone pair. Then what you have understood, in IF5 you have only one lone pair, right? So only one lone pair present. In the sense, what you can show its structure, it will be like iodine which has bound to 4 fluorine, right? So 4 fluorine you have, and one lone pair here. Okay, and one fluorine here. All right. So this is what the structure you have with respect to your IF5 molecule. So like this way, whenever the chemical bonding, that too with respect to VSCPR theory, already I had explained previously in my NEET session, right? And similarly here also you are going to apply your hybridization concept, and just you are going to consider with respect to how many lone pairs are present in a given molecule. All right. So this is what in the approaching the question. Okay, so now coming to your next question you have with respect to the statements. So the statement 1, statement 2 they have given. Now your duty is to find out whether which one is correct or both are incorrect or correct. Now coming to the statement 1, they have given that the boiling points of the following hydrides of group 16 elements increases in the order H2O, H2S, H2SC, H2T. All right. So the statement 2, what they have given, the boiling points of these hydrides increase with increase in molar mass. In the light of the above statement, choose the most appropriate answer from the option given below. So statement 1, statement 2, both are related to the boiling point of the hydrides of group 16 elements, that we know. The thing is, whatever the order they have given, whether it is proper or no. And in statement 2, whatever they have given, the increasing boiling point, why is it so? If they are considering with respect to molar mass, whether it is correct or no, so that is what you have to find out. Now, with respect to this question, what you have the answer, it is option D. So why is it so only option D? Okay, so just let us go in detail. Now, what they have given? They have given with respect to your boiling point, and that too in group 16 hydrides. So, group 16 hydrides where you have oxygen, sulfur, selenium, and tellurium elements, right? So, these are what you are getting in group 16, right? So, the hydrides already they have mentioned H2O, H2S, and H2SE, H2TE. So under the, I mean, down the group, the boiling point will be increasing, no doubt. But in case of group 16, whatever the water molecule you have, it will be involved in the hydrogen bonding. So it will be involved in the hydrogen bonding. That's why its boiling point will be increasing. Okay, that's why its boiling point will be increasing. So hydrogen bonding is the force where intermolecular force of attraction or else intramolecular force of attraction, which will be increasing where it is just holding two water molecules with each other, right? So because of that reason, some amount of energy must be needed in order to break that bond. All right, so in normal molecules, whenever we consider the hydrogen bonding, so that can be broken down easily. That force will be some kind of weak intramolecular force of attraction. But when you consider the two water molecules, so in between these two, so whatever these are the two water molecules, right? So whatever the hydrogen bonding you can see, it is bit difficult to break the bond, in the sense you are just spending some more amount of energy compared to remaining where you are going to consider the hydrogen bonding. So that's why the boiling point of the following hydrates, whatever they have given with respect to statement 1, they have given in reverse. So the statement 1 is incorrect. So one thing we concluded that statement 1 is incorrect. Now coming to your statement 2, what they have given? They have given the reason that is due to with increase in molar mass. So why is it so? Whether molar mass is really, it is mainly affecting the boiling point of hydrides. So that we have to conclude. So the boiling point of all the hydrides, whenever we consider that may be not only with respect to group 16, 17 or any other hydrides we are going to consider. So overall we know that when there will be increase in the atomic size and there will be molecular mass increase also, there is difference between the molar mass and molecular mass, right? So the molecular mass where the atomic weight of each and every element, whenever we go down the group, it will be increasing, right? So because of that reason, we do say that the melting point and boiling point of each hydrides with respect to 14, 15, 16, 17, it will be increasing. All right, so but in this case, one case we have the exceptionally in water molecule, the existence of this hydrogen bonding mainly affecting the boiling point. That's why the water molecule has highest boiling point compared to your remaining sulfur, selenium and tellurium. That's why the statement 1 is incorrect and statement 2 is also incorrect. Why is it so? The reason whatever they have given with respect to the boiling point of the hydrides is not proper. All right, so this is what the case we have. Now coming to your next question. The next question, they have directly asked question where diamond and graphite, their properties are being given. So the correct statement you have to choose in this question part: the diamond is sp3 hybridized and graphite is sp2 hybridized. So this is what the first option. Coming to your second option, both diamond and graphites are used as dry lubricants, and option 3 where diamond and graphite have two dimensional network, and option 4 you have that is diamond is covalent and graphite is ionic in nature. So if you know the properties of diamond and graphite properly, then this direct question can be quickly answered within a second. So just let us look at the answer what you can have, that is option A. So option A is the correct statement with respect to your diamond and graphite. So they have given it is sp3 hybridized, I mean diamond, and graphite is sp2 hybridized. So both diamond and graphite according to your answer, so option A is proper, means it is correct statement. Now coming to your option 2, both diamond and graphite are used as dry lubricants. Is it not so? So in case of graphite, this statement can be followed, but in case of diamond, it is not followed. So it cannot be used as a dry lubricant. That's why this statement is wrong. Now coming to the third statement, what they have given, diamond and graphite have two dimensional network. No, this is not true. So So both are having 3D network in them, right? So this is what the 3D network they have, that is three-dimensional network they have. So statement 3 is also false. Now coming to your option 4, the statement diamond is covalent and graphite is ionic, they have mentioned. No, both diamond and graphite both are covalent in nature. All right, so graphite is not ionic in nature, even this is covalent in nature. That's why while preparing all group chemistry you have to know their properties also. This is what the direct question they have asked. Now coming to your next question, you have again statement. So which statement regarding polymers is not correct? Even this is one of the direct question only. So what they have asked mainly, so the option A they have given with respect to thermoplastic polymers. So the statement is being given like this: thermoplastic polymers are capable of repeatedly softening and hardening on heating and cooling respectively. So this is with respect to thermoplastic polymers. And with respect to your thermosetting polymers, they have given the statement as they are reusable. And option 3, where the elastomers have polymer chains held together by weak intermolecular forces. And option 4 you have, that is fibers possess high tensile strength. So why is it so? Which option you are going to choose? Before that, just let us look at the answer, that is option B for this question, that two polymers, that is thermosetting polymers, are not reusable. So that is what the correct statement, but they have given they are reusable. All right, so why thermosetting polymers are reusable they have given, and why not they are not reusable? So the thing, we know that thermosetting polymers are already heavy branched molecules. I mean, they are cross linked to each other already. Suppose we heat, like we are heating the thermoplastic polymers. So thermoplastic polymers have the property, on heating they may become soft, after cooling they become hard, right? But in case of thermosetting polymers, this statement or the application of heat is not that much applicable, because when you heat the already cross-linked thermosetting polymers, again it becomes infusible, in the sense it will become more complicated whenever you place in a mold. When you apply, I mean when you apply some amount of heat, then it will not go whatever the property is being shown by the thermoplastic polymers, it will not shown like that. In the sense, it will be more extensively cross-linked to each other. That's why your option B is correct, where it is true, it is not correct statement, it is incorrect statement. All right, now coming to your option 3 and option 4, both are being given with respect to elastomers and the fiber processes. So this is correct statement. Okay, now coming to your next question part, you have with respect to organic chemistry part, where they have given some carbonyl compounds, that is in list 2 you can see. So this is what the list 2 you have, this is list 2, and list 1 where they have given directly their products. Okay, so now your duty is to take any carbonyl compound. So just let us consider with that may be your acetaldehyde, or that may be your acetone. Okay, so that is acetone. So try to just treat with your corresponding whatever they have given, NH2OH, RNH2, alcohol and HCN, and you are going to get some products here. Okay, so you are going to some products they have mentioned in list 1. So what will be your answer? So that you have to look into it. Okay, before that, just let us look at the answer what you will get here, that is option B. So option B you have the answer. Okay, so just let us try to get the overall answer with respect to each and every reactant and product whatever you are getting. So now coming to, you have hydroxylamine, amine and alcohol, HCl. Okay, so just let us move to next slide. You have here your answers. So you have firstly your NH2OH, right, that is hydroxylamine. So when you treat hydroxylamine with your corresponding carbonyl compound, so just let us consider this is R1 and R dash. So R and R1 and R dash can be anything here. Now, so just you are going to remove the water molecule, and what you will get here, so just you are getting C, this is R1 and this is R2, C double bond N, okay, and OH. So what is this? This is oxime, right? So this is what oxime we have got. Now coming to your next, what you are having alcohol, right? So you are having alcohol. So when you treat your alcohol with your corresponding carbonyl compound, so what you will get here? So you will get firstly hemiacetal. Okay, so first what happens here, so this alcohol can be cleaved as alkoxide anion and H plus, right? So just let me split it and act just attack on the carbonyl carbon center, and this oxygen will be grabbing this proton. All right, so now you have your carbon with oxygen and one hydrogen, and here R1 R2 you have, right? And another side you have your alkoxide ion, whichever it is being attacked. So just I'm not going to show here prime and all, because already it is mentioned at ROH. All right, so this is what you have got, your hemiacetal. So this is your hemiacetal. Next, what you are going to form, you are just going to attack another mole of alcohol. Okay, so just when we consider the another mole of alcohol, it will give me acetal directly. So just what you have to do, this proton will be gone with this OH as water molecule, and now carbon will be having one side OR, another side again OR, and then here you have your R double dash and here R dash. So this is what, this is your acetal. Okay, so now we have got with respect to your hydroxyl amine, with respect to your alcohol. Now coming to your two more reactants, what you are going to consider. So that is what, just let us consider in your overall slide. Okay, so here they have given further HCN also. Okay, so HCN you are going to treat with your corresponding carbonyl compound. So R1 R double dash you have, and again here you are going to split like H plus and Cn minus. So Cn minus will be attacking on your carbonyl carbon center, and oxygen will be grabbing this proton, and now you can see OH overall here, and here you have your R dash R double dash. All right, and you have here Cn. So this is what, this is your cyanohydrin, right? So cyanohydrin. So just by looking at your reactant and product side itself, you can answer easily, that is option B only, because only the option B they have given, that is HCN, that is A is giving me product. Whenever it reacting with your fourth part, list 2, so it is giving me cyanohydrin. So A, whatever they have shown with respect to 4, it is being mentioned only in your second option. All right, so now apart from that, what else you have your skip space formation also, right? So just let us consider the skip space formation. So with respect to skip space formation, you are going to consider amine. So you have your amine. All right, and you are just going to consider with respect to your carbonyl compound. So just let us consider, that is R dash and R double dash here. All right, so now what you have to do, again you are going to remove the water molecule, and you will get C triple bond N. Okay, and here R. Okay, so here this R is, which is already present on your nitrogen. So this is what Rn is 2, and here you have your R dash and R double dash. All right, so this is what you have got your skip space. Okay, so just let us go back with respect to your list 1 and list 2, whatever they have matched here. With respect to that, you have your option as option B here. Okay, so this is cyanohydrin with respect to your HCN, and your acetal is with respect to your alcohol, and skip space is with respect to your amine, and oxime is with respect to your oxime. Okay, so this is what with respect to each and every product and the reactant whatever they have given, you are going to treat with carbonyl compound, and you are going to get your cyanohydrin, acetal, oxime, and your skip space. All right, so this is what the answer part you have with respect to this question. Now let us move on with respect to your next question, that is statement 1, statement 2. Again they have given with respect to your aldehyde and ketones. Okay, so again here also the hydrogen bonding role comes. Now in the statement 1 they have given the boiling points of aldehydes and ketones are higher than the hydrocarbons of comparable molecular masses because of weak molecular association of aldehyde and ketones due to dipole-dipole interaction. So here statement 1, exactly they are focusing on the aldehydes and ketone, their boiling points with respect to hydrocarbons. All right, now coming to your statement 2, you have that boiling point of aldehydes and ketones are lower than the alcohols of similar molecular masses due to absence of hydrogen bonding. So statement 2, they are mainly considering with respect to the aldehyde and ketones are mainly considered with respect to your alcohols. Okay, so alcohols, so overall they are considering alcohols have higher boiling point compared to aldehyde and ketone, and then your hydrocarbons comes. Okay, so this is what the priority order they have given with respect to your statement 1 and statement 2. Now the options they have given with respect to statement 1, statement 2 and all, whether it is correct or incorrect, that maybe one is correct and another one will be incorrect. All right, so what option you can have with respect to this, I mean the correct option? So the correct option for this question is option C. So the option C, they have given that both statement 1 and 2 are correct. Yes, so obviously those are correct, because overall whenever we consider the boiling point specifically in the carbonyl functional groups, okay, so in case of carbonyl functional group, what we have the carbon which has attached to oxygen, that too we have C double bond O. So this C double bond O, if you want to show with respect to its dipole interaction, so how you can show? You can show like the oxygen will be bearing negative charge and carbon will be bearing positive charge, right? So this is what the dipole we can say with respect to your aldehyde and ketones. So whenever we consider these aldehyde and ketones with respect to your hydrocarbons, normal hydrocarbons are non-polar in nature, that already we know. But in case of aldehyde and ketones, their existence of carbon oxygen with negative and positive charge, that's why their existence of polar nature. Okay, their existence of polar nature. That's why these carbonyl groups or aldehyde ketones are having higher boiling point compared to your normal hydrocarbons. Now, so this is what the statement 1 they have given. Now, coming to your statement 2, what they are comparing? They are comparing your aldehyde and ketones with respect to alcohol. So with respect to alcohols, already we know that their existence of hydrogen bonding again. So when we consider with respect to your alcohol, that is ROH and your ketonyl or aldehyde group, okay, so here the carbonyl or I mean the aldehyde or ketone do not have any hydrogen bonding that much whenever we consider with respect to alcohol. No doubt there might be existence of the hydrogen bonding in aldehyde and ketone, but only the lower hydrocarbons will be having, I mean the methanol and all, okay, methanol, methanone, there might be having the hydrogen bonding. But when you increase the hydrocarbons, that too on the aldehyde and ketones part, their existence of no hydrogen bonding, okay, so there is no hydrogen bonding overall, and that's why their property is changing from gaseous phase to liquid, like that, okay. So just because of this and because of this reason the statement 1, statement 2, whatever they have given, both are correct, and option C here, I mean the option C is correct here. All right, so just let us move on with respect to our next question. Okay, so the next question you have, that is match the following. Again, list 1, list 2 they have given with respect to your ores and composition, and even here it is direct question. So what is your answer with respect to this question? That is option D. So option D, where one thing what you can notice here is in all options they have given, at least in 3 options they have given fourth, that is D. I mean the kaolinite, its composition they have given Al2OH4 and CSI twice O5, right? So in at least 4 options they have given, that is D4, and this is what the direct question, I mean direct answer we have with respect to kaolinite, right? So if it is so, then we have to correlate with respect to the remaining ores, okay. So ores, we know that hematite normally that is Fe2O3, right? So Fe2O3 we already know, but the thing that there might be some confusion with respect to your calamite and magnetite, right? So magnetite we know that it will be Fe3O4 and calamine will be your zinc carbonate. All right, so with respect to this, if you compare, your option D will be correct answer here. Okay, so your option D will be correct option. Now coming to your next question, you have that given again 2 statements, okay. So the statement 1, statement 2 they have given with respect to your primary alcohol, secondary, tertiary alcohol and their distinguishing test. So statement 1 follows like this: in Lucas test, primary, secondary and tertiary alcohols are distinguished on the basis of their reactivity with concentrated HCl, ZnCl2, which is known as Lucas reagent here. So this HCl and ZnCl2 is known as your Lucas reagent. And the statement 2 follows like this: primary alcohols are most reactive and immediately produce turbidity at room temperature on reaction with Lucas reagent. So overall, whenever we consider with respect to your Lucas test, that too for distinguishing test for the alcohols, the primary, secondary, tertiary alcohols can be distinguished based on their turbidity formation. So when exactly, I mean, when immediately the turbidity is released in a test tube, then we can say that might be tertiary alcohol, right? But with respect to statement to what they have given, the primary alcohols are reactive, I mean, most reactive, immediately produce turbidity at room temperature. It is not possible at all. Primary alcohol will not produce turbidity at room temperature, but only the tertiary alcohols can produce the turbidity immediately. That's why your statement 2 is wrong. When you consider with respect to statement 1, it is correct. So the Lucas test, whatever we are following, that using the Lucas reagent HCl in ZnCl2, it is specifically used in order to distinguish your alcohols, primary, secondary, and tertiary. That's why your statement 1 is correct, but statement 2 is wrong. So in which option you can see that is statement 1 is correct, but statement 2 is incorrect, that is in option A. All right, so just let us look at the option, that is option A is correct for this question. All right, so now coming to your next question, you have that with respect to K-4. So the question follows like this: in the neutral or faintly alkaline medium, the K-4, okay, the K-4 oxidizes iodide into iodate, and the change in oxidation state of manganese in this reaction from. So just they have given one reaction where you are going to specifically identify the oxidation state of your manganese in K-4, and after the formation of your iodate, I mean, it is mainly oxidizing the iodide, that is iodide, I mean I minus to your iodate, that is IO3 minus. Okay, so just you are going to consider with respect to its oxidation state. So just let us write its reaction, that is K-4 you have. Okay, K-4, when you oxidize I minus, okay, so just let us consider I minus also here only. So you have your I minus and you are going to oxidize it into your IO3 minus. Apart from that, you have released MnO2 also. Okay, so you're just mentioning alkaline medium. Okay, so here K-4 where manganese is in its +7 oxidation state. Okay, so if you consider with respect to your IO3 minus, here it is in its +4 oxidation state. All right, it is in its it is not IO3 minus, it is with respect to your manganese. So here you are going to consider with respect to your manganese, right? So here the manganese you have, its oxidation state will be +4. How it is +4? Oxygen which will be giving 2 charge, right? So 2 charge, so overall it will be like you have -2 into 2, that will be -2 in the beginning. So if you shift this to your right hand side, it will be equal to +2. Okay, so that's why what, so +2 you will be having, so twice you have, that will be +4. All right, so overall you have that is -2 into 2, so you will get here that is -4 in the beginning. So you are going to shift right hand side and you will get your answer as +4 here. All right, so this is what with respect to manganese you are going to calculate the oxidation state. So K-4 upon oxidation, that is it is oxidizing I minus to IO3 minus and itself getting the oxidation state as +4. So overall it has +4 here. All right, so this is what the question you have, and the options if you look at here, so you have the option C where +7 to +4 you have overall. All right, so this is what your alkaline medium question. Now coming to your next question you have, that is last question with respect to your order of energy. So that too in coordination complexes they are mainly asked. So they have given 3 complexes A, B, C where only water ligand and the ethylene diamine ligand they have given. And now the question follows like this: the order of energy absorbed which is responsible for the color of the complexes. So 3 questions where the 3 complexes are being given and their color of the complex is due to, and their order you have to consider. Okay, so in order to know the color of the complexes, we know that specifically in coordination complexes, the coordinating ligands also mainly mainly specify or influence the color of the complexes. Okay, so when we consider the strong ligand or weak ligand also, it influences the color of the complexes. Why is it so? How exactly they are influencing the color of the transition metal complexes or else the coordination complexes? That is due to the strong or weak ligand mainly influencing the splitting energy of d orbitals. So when we consider the metal d orbitals, its d orbitals has to be splitting, right? So whatever the strong ligand we have, it has higher energy splitting. Okay, so the delta naught will be more whenever you have strong field ligand, but when you consider with respect to weak field ligand, it will be less. All right, so with respect to that, whenever you consider the strong field ligand, they absorb high energy at blue violet light. So it will be so the color of the complexes will be exhibiting like yellow, orange, red, like that. But when you consider the weak field ligand, so weak field ligand, that will be absorbing energy in the light like yellow, orange, red light, and it will be exhibiting the color like, and the color of the complexes will be blue, violet, or indigo. So like that it will be vice versa. So now they have given three complexes, that is nickel with H2O twice and En twice. Okay, and nextly they have given that En twice. Okay, so here you have four water molecules but two ethylene diamine, only one ethylene diamine. And in case of your third complex, you have three ethylene diamine. So you have three ethylene diamine in complex C, and in case of complex B, you have only one ethylene diamine, and in case of complex A, you have two ethylene diamine. Okay, so we know that water is already weak field ligand. All right, so weak field ligand in the sense what, the splitting energy will be less, right? So now what happens, the ethylene diamine, whatever you have, it is strong ligand. That's why in the structure, I mean the complex C, whatever they have given, we have two ethylene diamine, right? So because of these strong ligands, three ethylene diamine ligand, because of that reason the color of the complex will be more, right? So the energy absorption will be more with respect to your complex C, and that's why your the complex C, whatever you are going to consider, so that will be exhibiting color of the complex at its highest rate. I mean, it is absorbing energy more. Okay, so now you have three, then you have your 2 and 1. So here you have in your option A 2 ethylene diamine. So that's why I have to consider your 2 ethylene diamine first. And at last you are going to consider the complex which is having only one ethylene diamine. So I am going to consider like this. So the priority order 3, 2, 1. Right. So the answer will be what? Your CAB. So what you have, that is C first, and then your A, then will be your B. So why you are considering B at last? Because you have four water molecules, I mean four weak ligands you have, but only one ethylene diamine, that is one strong ligand you have. So the energy of absorption, whatever you can see, it is not at its highest rate, or else it is not that much compared to your C and A complexes. All right. So this is what the question part you have with respect to your coordination complex series. Okay, so in case of your spectrochemical series also, whenever you consider that too in the weak ligand and strong ligand field series you have, right? So there also ethylene diamine comes first, then water. Okay, so already we know that water is weak field ligand. That's why it will be not affecting the color of the complex that much compared to your strong field ligand, that is ethylene diamine. So with this, I'm going to end my session. And finally, thank you so much, guys, everyone. And definitely, you are going to fulfill your all dreams, and you are getting your positive result also. Again, we'll come up with few more NEET sessions which are helpful for you. Till that, thank you. Bye bye. And don't forget to subscribe our Biotecnika channel, and we will be coming with beneficial videos for you.